Alright, welcome to our lesson 13.3. This lesson is going to be very similar to our lesson about drawing diagrams in curved mirrors, but we're going to be applying our knowledge to lenses. So this is 13.3 in your textbook if you want to reference that later. So just to recap what we did in that lesson about mirrors, we looked at both concave mirrors and convex mirrors. Now there were two other names for those mirrors. So another name for a concave mirror is converging, and another name for a convex mirror is diverging. Those descriptions have to do with what's happening to the light. So what happens in a concave mirror, as we saw, when light hits the mirror, it gets reflected back, but not only does it get reflected back, it gets reflected back to a point. So the light rays tend to meet together, right? It converges at one point. That's not the same in a diverging mirror. What happens in a diverging mirror is when you have light hitting the mirror, the light then gets spread apart. It's still reflected, but it gets spread apart. So I want you to take that terms converging and diverging, and we're going to apply it to lenses. So for a converging lens, the light, instead of it being reflected back for a mirror, it passes through the mirror, and then it comes towards a point. For a diverging lens, the light hits the lens and then it's spread apart. We're going to look at that in detail when we're looking at our diagrams. So let's first take a look at converging lenses. These diagrams are going to be just like our concave mirror diagrams. There are similarities, and we're going to do exactly the same thing as we did previously, where we're looking at different scenarios. Before we get into that, we're going to need to get our terminology really down well. So the first thing we're going to draw is a line that looks like this. This line is still called the principal axis in lenses, right? And our key difference here is that instead of drawing a mirror, we're going to draw a lens. This is a converging lens. Now, this is, if you look at the shape of it, this can get pretty difficult when you're drawing ray diagrams. So if we say that a light ray hits the lens, it's going to be quite difficult because all of those edges are curved. So instead, what we tend to do is draw a dotted line towards the center of this converging lens. Now, when we say light hits this lens, we are talking about light hitting the dotted line. So it's much easier when we're drawing diagrams. And I also want to draw your attention to the very center point. This is called the optical center. This is a point that we're going to reference in the future as well. Now, something else that we are going to take from our diagrams in mirrors is our focal length. Now, if you notice, a key difference between lenses and mirrors is that in mirrors, all of the diagram parts are towards one side or the other. That's because the light is reflected, right? So it hits the mirror and then it's reflected back. In a lens, we've got two different sides. The side that the light is coming through and the side that the light is going into. So we have to reference the focal length on either side. And we do this using two different points. So on the right side, you've got F, just F. On the left side, you see an F and then an apostrophe. That is because you are talking about F prime. And when I'm referring to F prime for the rest of this video, I'm referring to the F apostrophe that's on one side of my lens. Now, F is still the focal point, and the distance between that optical center and F prime, and the distance between that optical center and F are both the focal length. Okay, we also have another two values on either side of my lens. On the left side, I've got 2F prime. And then on the right side, I've got 2F. Now, just like that label suggests, 2F is double the focal length, and 2F prime is double 2F prime, which is the same. So that is all the terminology that you need when we're talking about diagrams for converging lenses. Now, in some ways, these diagrams are a lot easier because you're only going to need to draw two, and they stay consistent pretty much throughout most lenses. So just like we talked about in our mirror diagrams, we're going to look at different scenarios. So we're going to look at if the object is before or beyond 2f prime, where's the image going to be? We're going to look at if it's between 2f prime and f prime. So there's different scenarios that we're going to move through in which the image appears at different places. And then when we draw our image, we're going to use our SALT, our size, attitude, location, and type in reference to the object to be able to describe an image. So let's actually get into our first scenario. Our first scenario is when the object is beyond 2f prime. So that means it's beyond 2f prime on the left side. My first set of lines that I'm going to draw is the line that starts at the top of the object and goes towards the lens. So there it is. So I'm drawing this line, and every time I draw this line, it's got to be parallel to my principal axis, right? If this line is slanted, that's going to affect the way that your image turns out. So you start off at the top of the object, it hits the line that we drew for our converging lens. And then, like I said, for converging lens, those lines get focused into one point, right? It's a converging lens. So this line, as soon as it hits the lens, is going to then move towards the focal point. So we're going to draw that line at that point through F, continuing on. Okay, so that's my first set of lines, one of two. My second set of lines starts at the top of my object. It's going to go through what we talked about as being the optical center early on, and then it's going to continue on. So there is that line. Now, exactly like in our previous diagrams, wherever these two lines meet, that is where my image is going to be formed. Another distinction, I don't know if I explained this well enough in my mirror diagrams, but because the lines of the light start off at the top of the arrow, wherever those lines meet, that's where the top of my arrow will go. So if I keep the top of my arrow here, it means that my image is going to be upside down. That's why we have an upside down image here. So I've just drawn my image where the lines meet. Now I'm going to use SALT to describe it. So if we're talking about size, this image is smaller. Attitude, it's inverted. Location, because I've got reference points F and 2F, I can say that it's between F and 2F. And type, just like we did in our ray diagrams, where light meets or where those two lines come together, if an image is formed there, we know that it's a real image. Now, this might make a little bit more sense to you when we see a virtual image. You'll see that our mind is able to extrapolate where those lines will meet and then create an image. So that's where our difference lies. So for now, because these light rays are actually meeting at a location and that's where our image is formed, we're going to call this a real image. Let's look at scenario number 2. In scenario number 2, the object is at 2f prime. So I'm going to draw my arrow right on there. And my two lines are exactly the same, or my two sets of lines rather. So I'm starting at the top of my object, moving towards the dotted line, and then it's moving towards F on the other side. Same other second line here, starting at the top of the object, moving towards the optical center, and then going on. So those two lines happen to meet exactly at 2F. And this might be a little bit hard for you to draw on your piece of paper, but try and line up the top line. It's very important that this is parallel, and it's very important that this meets the optical center. So if you're getting those two right, where those lines meet should be right underneath 2F. So if you're describing the image that I just drew, the size is going to be the same. The attitude is inverted. the location is at 2f, and just like in our previous example, the type is real. The image is formed where those two lines are actually meeting. Okay, let's look at our third scenario. In this case, the object is between 2f prime and f prime. So somewhere in between there. The lines are exactly the same. Parallel line going from the top of my object to the lens, coming back through f, and a line starting at the top of the object going through the optical center. Where those two lines meet, that is where the top of the arrow will go, hence making the image upside down. If I'm describing this image, the size of it, it's clearly larger. The attitude is inverted. The location is beyond 2f. And the type is, again, real. Perfect. Scenario number 4, the object is at f prime. So if I'm drawing an arrow right on f prime, I'm going to draw the exact same lines. Top of the object to the lens, from the lens towards f, and then I'm going to draw a line starting at the top of the object, going through the optical center, and then continuing on. Now, something that you'll notice in this scenario is that if you draw these lines exactly correctly, they are going to be parallel. And what happens if they're parallel is that they're never going to meet. So if the lines don't meet, an image can't be formed. And that's what happens in this scenario. Because those two light rays will never meet, no image is produced. Okay, and that's why in our previous examples, we have to draw our image where those lines meet, because that's where that image is formed. In this case, the lines don't meet, which means that no image is formed. Now, this is actually something about lenses. This is how you would find the focal point of a lens. You would hold up an object and see where there's no image produced. That is your focal point, and that you can use that as a reference point for that particular lens. Okay, so moving on to our fifth example for converging lenses. Our object is in front of f prime. So I'm going to draw my object, my arrow, in front of f prime, or in between f prime and my lens. My first line is the same, so I'm going to start at the top of the object. It's going to hit the lens, and then it's going to again move towards f on the other side. My second set of lines is going to go from the top of the object through the optical center and on. Now, if I take a look at these light rays, they're not parallel, right? Which means that they do certainly meet at one point. However, if I keep going towards the right side, if I just continue on these lines forever and ever towards my right, they're not going to meet. They're just moving farther and farther apart, which means that if I would have to extend these lines towards the other side in order for it to identify where those lines actually meet. So let me just repeat that one more time. So if I'm drawing these diagrams, these lines as is, and I continue these lines forever, they're not going to meet because they're going farther and farther apart. What's going to happen, or what I'm going to need to do, is extend these lines backwards towards the left side to finally identify where they meet. So if I draw these lines back, I know a location at which both of those lines meet. That's exactly where my image is going to be formed. So this is the one. The lines are still the same in this one, right? So we drew the exact same lines. We just had the added step of extending them back to see where those lines come together. So my image formed exactly where those lines meet. So let's describe the image in comparison to the object. Now, this might be a little bit confusing, so I'm just going to clarify. So this is my object, and this is my image. So if I'm comparing the two, the size, the image is clearly larger. The attitude, it's not upside down, right? So it is upright. So again, let me just go over why the arrow is upright in this case. Where the lines start, so where these lines start is at the top of the arrow. That means wherever they meet, the top of the arrow will go there as well. And because it's in this position, it just happens to be upright. Location, we can say behind the lens, right? Because it's not on the other side, it's behind the lens. And the type. Now, in this example, we've got these lines. They're not meeting, right? We had to extend it back, which means that what we do when we look at this lens, or look through this lens rather, is that we are extrapolating. Our brain is able to extend these lines backwards and then see that image there. So that is why this is a virtual image. So the light rays are not actually meeting. We have to extend those lines back, which is why we draw them as dotted lines, right? So anytime that you're not, you have to extend these lines back, we're drawing them as dotted lines. If you're talking about a mirror, we always refer to anything behind the mirror to be in a dotted line, right? So it's sort of the same scenario here because you're extending them back in the opposite direction. You're drawing them as dotted lines. So those were our 5 scenarios for our converging lens. So if you started off before 2f, you had an image if you started off with your object beyond 2f prime, your image always appears between f and 2f. If you started off at 2f, your image 2f prime, your image will always be at 2f. And so on and so forth, until you get to a point where your image is at 2f prime, in which case no image is produced. If you go forward, if you bring it even closer, what ends up happening is that your image appears on the same side or behind the lens. So you just want to sort of understand that there is kind of a pattern that's taking place, right? If you're moving from farther away, the image appears small. If you're coming closer and closer through the lens, you'll see that the image gets bigger and bigger until a point where the image is no longer produced, and then the image becomes virtual, right? So it's kind of a pattern. Try and understand that to the best of your ability. And now what I want you to do, try and fill in this chart. So I'm going to let you pause here, fill it in, and then I can show you the answers. Okay, so this is our completed chart. This is all of the information that we had for each of those scenarios, just filled into a chart form, just so that you can see some of the trends that are appearing. Okay, now let's move into diverging lenses. Just like we did for converging lenses, let's look at some terminology. So first example, obviously, instead of using a mirror or a converging lens, I'm going to draw out my diverging lens. I have my principal axis, that's still the same. And just like I did for my converging lens, I'm going to draw a dotted line straight through the middle. That is the reference point that I have for when I say that a light ray hits the lens, right? So that's going to be the point at which my line will stop when I'm drawing these diagrams. I still have f and f prime. The only difference is that in a diverging lens, the f is on the left side and the f prime is on the right side. Still the focal point, still the focal length. I've got 2f and 2f prime. Okay, so this is just the terminology that is in reference to diverging lenses. Okay, so the good thing about diverging lenses that you might like is that there's only one scenario, because your image is always going to be appearing in a similar fashion. So I'm going to start off with my line. I'm going to start off at the top of my object, go towards the lens. I'm going to stop at that dotted line. And then I'm going to extend that over to the other side. Remember that this is a diverging lens, right? So the light ray is sort of going off or diverted or spread apart. Now, how do I know how to draw that line? I just have to line it up with F. Okay, so let me just go over that one more time. So I'm going to start off at the top of my object until I hit the dotted line. And then I'm going to line up where that line hits the dotted line with my value of F and then draw a line. if I'm just like I showed you in that last example for converging lenses, if I'm moving my line backwards, right, behind the lens, I'm going to draw it as a dotted line. My second line stays the same, starting at the top of the object, going towards the optical center. That's still true for a diverging lens. And that is it. Where those two lines meet, that is where my image is going to be formed. Again, because some part of those two lines that are meeting is something that our brain is able to visualize. That's why we consider this to be a virtual image. So it's not a real image, it's a virtual one. So let's describe it. So the image is smaller than my object. The attitude, it is upright. The location, it is the same side as the object. And the type, it is virtual. Like I said, those lines aren't actually meeting, right? There's that green line, it's being extended back when we look at it, and we're interpreting that information, which means that this is a virtual image. Just like we did for that previous example, because there's only one scenario, this becomes a very easy chart to fill out. Size is smaller, attitude's upright, location is same side as object, and the type is virtual. That's it for this particular lesson. You don't have any homework, but please, please, please make sure that you understand each of those scenarios really well, including the light lines.